In this video series, we will give a basic structures for Riemannian manifolds. Of course, it is not possible to give all the structures for the Riemannian geometry, but we will give at least some very important basic structures for the Riemannian geometry. So first, let me define the Riemannian metric and Riemannian manifold. So Riemannian metric and Riemannian manifold. So first, let M be a differentiable manifold. G, let's say Km cross product Km to C infinity Mr. So these differential functions on the manifold. So and X, Y, Z belongs to this set of vector fields on M. If G is bilinear, so let's say 1. So what does it mean? It means it is linear for the first part and linear for the second part. So G, let's say lambda 1 times X, mu 1 times Y, Z equals lambda 1 times G XY and mu 1 times G YZ. So this should be Z. So here lambda and mu, lambda 1 and mu 1, again they are differentiable functions on the manifold. And this is first part. The second part, linearity, y plus, let's say, 2z. So this one is also 2. So you have lambda 2 times xy plus mu 2 times yz, no, xz. So here again lambda 2, mu 2 are differentiable functions. So first G will be bilinear, and second G is symmetric. So it means Gxy should be Gyx. And 3, G is positive definite. Positive definite. So it means if Gxx is bigger than or equal to 0, equals 0 if and only if x itself should be 0. So these three conditions are satisfied, then G is called Riemannian metric. And this Mg is called Riemannian manifold. So you see, we put this inner product on the tangent space, or the space of the vector fields. So now it's possible to define the length, angle, and so some geometric notions. So the length of x is defined x. Now because we have a g, so g xx. The angle between, let's say, x and y, so it will be cosine of theta and gxy over the length of x and length of y. So we make the tangent, the space of the vector fields as an inner product space. So basic example, consider canonical inner product, let's say this one, on R of 2n. So we know that if x equals x1, xn, rn, and y, y1, yn, r2n, then the inner product of x, y is I goes from 1 to n, x I times yi. So it is easy to see that this is a bilinear and symmetric because you are multiplicating xi and yi number. And also it is easy to find the positive definity. Indeed, if you take this one, xx, you have x1 square, x2 square, xn square. So this is equal to 0 if and only if x equals 0. And generally this one is, if x is not 0, then it is bigger than 0. So that's why we call this Rn, and this inner product, we denote this one E to n, and we call this one Euclidean space. Now, let's say this Ng Riemannian manifold. So we choose this one, x1, xn, orthonormal frame. So now the orthonormal is meaningful because here we define the theta, cosine theta. So it means it is possible to define the orthogonality. So that's why we choose the orthonormal frame. So if you have this one, you can choose the dxn as dual orthonormal frame. frame. So this defining this one, xj is chronicle ij. Now if you choose, let's say x, y belongs to Km, the vector field on this one, then we can write x as I goes from 1 to n, xi. And if you write the dxi, take dxi x, then you have this xi. So now consider this one, gxy. So because we can write this one in this form, I goes from 1 to n, dxi x d. So let me write this one because this xi, so I forget this one, xi, and similarly j goes from I to 1 to n, dxj y xj. So these parentheses. Now we can write this one in this form. So ij goes in same index. So you can write g xi xj and dxi x dxj y. Or if you put this one gij, then you have this one. So gxy gij dxx dxj. Or because of this is correct for every x and y, we can write in this form, ij gij dxi dxj. Or you can use Einstein summation, then we can write j dxi dxj. So this is the expression of the Riemannian metric. So actually this implies the Riemannian metric, these components, this one. To see this expression more clearly, let's consider this one. So suppose M be a Riemannian manifold and dimension of this M we consider 2. So we choose E1, E2 orthonormal field and DE1, DE2 dual orthonormal field. Then if you consider the x and y as a vector field on manifold, then we can write x, x1, e1, x2, e2. Similarly, y, y1, e1, y2, e2. So again, if you write the DE1x will be x1, DE2x will be x2. So similarly, DE1y will be y21 and DE2y will be y2. So now if you write this gxy, then we have this one, x1, y1, g, e1, e1, plus x1, y2, g, e1, e2, plus x2, y1, g, e2, e1, and plus x2, y2, g, e2, e2. So instead of this one, we can write DE1x, DE1y, G11 plus DE1x, DE2y, G12 plus DE2x, DE2y, G21 and plus DE2x, DE2y, G22. Now you can write this one. So let's say this gxy. So first you have this row matrix DE1x, DE2x, then here you have this one G11, G12, G21, G22. Then you have this column matrix DE1y, DE2y. So you see this one. This is the matrix for the metric. So if this is the positive definite, this matrix, then we can determine this G is metric or not. So it will be enough to check this matrix to clarify that this G is a metric or not. Now if you consider this one, let's say R2 and our canonical metric, this one, then because in this case we have this matrix, G11 will be 1, G12 will be 0, G21 will be 0, and G1 will be 0. So if you write in this form, then you have this one, dx1 square, dx2 square. So this G11 here, G22 here, the other parts are 0. Actually, we are imitating the Euclidean space, and if you consider the Euclidean space, we have some spatial covariant derivative. So that's why we can wonder, is there any spatial covariant derivative or for the manifold linear connection for the Riemannian manifold? Actually there is. So we will mention about this theorem. let Mg be a Riemannian manifold then there is a unique, right? A unique linear connection or maybe I should write in this form, unique torsion free and compatible linear connection on Mg. So what does mean the torsion free? It means your Txy, nabla xy, nabla yx minus bracket will be 0. The second part, compatible. So you have this one. First, let me write this one. So we have this one. Or we can write in this form, right? So this is some background information. You have this one. Bracket will be in this form. And x, g, y, z will be g nabla x, y, z plus y nabla x, z. All these x, y, z are vector fields on the manifold. So we will give the uniqueness and the existence of this connection. First, okay, let's say proof. The first one is uniqueness. So first, let me remind, if we have metric, Riemannian metric on the manifold, this is the unique metric. So in this case, we did this Riemannian manifold, and if you choose another metric, then you can obtain another Riemannian manifold. So if you have only, when you determine the metric, actually you determine the unique manifold, Riemannian manifold. Okay. Now first consider this one, g nabla xy z by using this one. I can write this yz minus y nabla xz. So then x g y z, if I use this one, the second part, then I'm using the linearity of this g, then you have this one. Okay, Okay, now we will use again the compatible metric. So let me put here YZ, GY, XZ, and here you have Z, YX plus nabla ZYX. So now we will use the again torsion free connection. So then we have this one. This part will be same. So I will put this one. So this one now GZYX plus YZX. Again, now we will use the metric compatibility for the G. So then we have this one. Okay, let me continue here. So again, this part will be same. Okay, let me check. Choose again. Okay, now the last part, I will apply the metric compatibility. So then you have ZX minus Z nabla YX. So the last part, we will again use the torsion free property. So then we have this one. Again, this part will be same. So I will choose this one. So we have this one. And minus okay, now look at this one. You see this part are same but opposite sign. So we can write two times nabla XY Z equals, so I will choose this part. So we have this one. If you look at this last expression, this one, we have only G. So 2 is a number, so it doesn't matter. So I just forget this one. Yeah. Or if I write this one in this form again, X, G, Y, Z plus Y, G, Z, X minus Z, G, Y, X, and then the bracket parts Y, X, Z So x, z, y. So these are parentheses. And minus z, yx. So you see everything is dependent on this g, because g is a unique, so nabla is unique. So the existence, so let's say this one is called, we call the star. If defining this nabla by star, nabla satisfies the properties, all properties of linear convection. So this implies that we can choose or we can construct this nabla linear connection. So this one is called the Kosul identity. So in this form, nabla is called Levi-Civita connection, Riemannian connection, or sometimes they call the compatible connection. So this Kosul identity is very important in Riemannian geometry, because many properties of the Riemannian geometry obtained by this formula.